Hello everybody, so I understand that I'm the last session. And so for you brave people that waiting now, I hope that you find this presentation interesting. My name is Avi Alkobi, I'm Director of Technical Marketing from Manox Technology. Who here in the audience is familiar with Manox Technology? Can raise his hand. Okay, so let's do a short introduction. This is a 3,000 people company, quite a matured one actually, started in 1999. Focusing on the silicon, on the ASIC. We are an ASIC company doing InfiniBand. InfiniBand is a different technology. We will not talk about it right now. Approximately 7 years ago, we started to launch also our Ethernet networking products. So basically, we're competing against the big boys, Arista, Cisco, and others in the data center environment with a little twist because, and here is an anecdote, Manox is actually the only company in the world that is doing all the network component PCI to PCI. It means that we are doing designing, producing, developing NIC cards, cables, switch, cable, NIC card. So why is that so important? Because it gives us some kind of capability to talk to a different kind of audience, if it's storage, compute, network, and provide a different vision about what is the purpose of each of those components and what are the features that needs to be implemented in each of those components on the physical network to provide the best performance. So we're going to talk about kind of a combination of cloud and artificial intelligence. Before we start about that, let's just go through some of the buzzwords and try to explain them. So when talking about artificial intelligence, you can actually divide it to two kinds. The first kind is called general AI, and it's kind of a thing where we'll try to get machine act and sometimes even look like human beings in all the aspects. So I think that one of the obvious examples is like a human-like android. Right? So it will act and do everything that a human being will do. Is there an Android in the audience? Okay, there are no Androids, so that's good because you can believe me that it's pretty hard to do that. And science has actually understood that it's a pretty difficult task. So there is another approach which is called narrow artificial intelligence, and this is basically means that let's take specific actions, specific tasks that human beings are doing and let machines do that the same as human beings are doing that and even better. And this is something that we can work on and we can achieve. Machine learning is an approach to achieve artificial intelligence. So I think the best to kind of to understand this concept is kind of spam filtering. The idea is basically you are taking data, you are probing it, and you are getting to some kind of a conclusion about the outcome that should happen in this world, okay? And deep learning, coming from the big data, is basically an approach to achieve machine learning, and that means that we're taking the idea of this algorithm of probing the data and getting to this conclusion to the second level. It means that we are using big data to do that. And we are creating something that which for human beings is very simple, what is called basically neural network. So for example, if I'm driving my car and I see a deer jumping into the track, I will immediately maybe shift the steer wheel or press the brakes and so on. And if we want a machine to do that, we can create a very complex algorithm. It would be like if, else if, else if, else if, else if forever, okay? Or we can use deep learning actually to do that and collect this huge data and create this neuron between the different scenarios and the outcome. So if we create enough large neural network, then we're actually creating something that is called machine learning and artificial intelligence, basically narrow AI. So after we understood this concept, now let's see how does it work. So the type of workloads that we are seeing in AI, we can actually divide them, let's say, by two. The first part is the storage, is the big data part. And we see all kinds of different companies that are providing those kind of workloads. And the other one is the machine learning protocols or infrastructures that I think my colleague before me already mentioned. The important thing is to understand about those kind of workloads. Those workloads usually are working on bare metal. On the other hand, if you want to take this kind of workloads and actually expose them as a service, then we need to think about scaling out, multi-tenancy, and doing it as a service. And that brings us actually to a different part of this solution, which is the cloud solution. And for that, basically, we need to look at the infrastructure of the network infrastructure and talk about cloud from the cloud perspective. And I will focus more on the VXLAN part and the Rocky. So essential ingredients that we're going to talk about, and basically all this presentation will follow up those 4 ingredients. The first one is that we need very good performance, because this is what AI needs. If you're talking about GPUs or big data, you need a lot of bandwidth, you need low latency, you need other factors, and we're going to focus on RDMA in that aspect. The second one, if we're talking on the network virtualization part, then we need multi-tenancy because we're providing something as a service. We need also to be a flexible network because our customers will come with their own IP, and we need to be flexible enough to actually serve all our customers. And the third one is seamless orchestration, because we saw that there are workloads that are bare metal workloads versus a virtualized environment, and we need to somehow marry them. Okay? So we'll see how we can do that, and we're going to focus here about OpenStack and about EVPN. And the last part, of course, if there is no telemetry, we are in a big trouble, right? So we need telemetry, we need to support SLA, and we need to make it more application-centric. Let's go for number 1. Okay, who here is familiar with RDMA? Okay, we have some brave people here. Good. So let's talk about this concept that is called RDMA. So RDMA basically is the different way versus TCP to copy memory from one machine to another. So if working on the TCP way, TCP/IP way, this is the usual way. Basically, it means that you are opening a socket, you are going through the hypervisor, through the kernel, to the TCP/IP stack, to the NIC card, from a NIC card to the other NIC card on the other machine, and then back on the TCP/IP stack to the application level. Now, if you are doing 10 gigabit and you are okay with retransmission, everything, that's okay. But if 2 GPUs are working together, or NVMe, which we'll mention in a few seconds, very fast storage, then you have a problem, because it will not work, because your device is very strong, but your network is very weak. So what RDMA is saying basically if you want to copy memory from one machine to another, you should not involve the CPU at all. You should not involve your stack. What you need to do is basically from the application directly copy it to the NIC card to NIC card, and back to the application. So if you look in YouTube from Mellanox 100 gigabit RDMA, you will see that we can copy memory from one machine to another, running 100 gigabit on the network with 0% CPU. And the reason is simple. The CPU is just not part of this equation. And that's very strong, because that means 2 things. First of all, we can actually reach the bandwidth. And the second thing is that since we are not using CPU for the network, we have more CPU for the application. And CPU is a very expensive part, right, on our infrastructure. So this is RDMA. It's called also Rocky, which is RDMA over Converged Ethernet. RDMA came from an InfiniBand world. We actually kind of invented it, and now it's part also of the Ethernet world. Okay, so with RDMA, and I mentioned that, we're going to get better performance, better throughput, better fairness between the users. Again, the reason is very simple. We are not tied to some constraints that we have as part of our hypervisor. Everything is working directly on the network. And also the CPU utilization is very low, which is good for AI. Let's see some examples for when are we going to use RDMA. So one example is called GPU Direct. So in the machine learning, when GPU talks to another GPU, again, using RDMA, it doesn't have to go through the stack. It just can go directly from a NIC card to a NIC card, and that basically boosts the performance. There are some nice benchmarks from TensorFlow, Caffe, and Paddle. All of them are using GPU direct, and you see clearly the difference between using TCP/IP to GPU direct with RoCE. Another example, which actually is not from the artificial intelligence world, it's actually from any world, because NVMe today is the fastest deployed storage probably. We are looking now at Optane to come in, but let's say till now it's the most deployed fast storage. And NVMe, I'm not a storage guy, but basically it means that you are cutting some old connectors, making your flash storage work very fast, but this is on the local level. If you want to run NVMe over the fabric, that means again copying memory from one NVMe to another NVMe, then you are doing something that's called NVMe over fabric. NVMe over fabric actually means NVMe over RDMA. Okay, so the idea is simple, as I said, just bypassing the TCP/IP, going directly from storage, target initiator, from the storage directly to the NIC card, other NIC card, and back on. So now, that's very nice, but till now I mentioned when talking about RDMA the NIC and the application. And this is actually, those are actually the two requirements to run RDMA. First of all, you need an application that knows what is RDMA. That means that it's using something, it's not called socket, it's called verbs, different API, and this is number one. Usually, if you will use RDMA, it means that you bought a solution that is already implemented with RDMA. For example, Pure Storage have it in the new FlashArray//X, Accelero, E8, Microsoft Storage Space Direct. There are many, many other examples. Nutanix, for example, are doing it. So it's actually across the industry when it comes to NVMe over fabric. So probably you will use such a solution later on. We hope that eventually Mellanox will do it and complete the work around Ceph and enable also RDMA over Ceph, and then you will see also the benefits there. Anyway, application is one. The second requirement, as I say, it's the NIC card. So you need the NIC card that actually do RDMA, hardware RDMA. This is basically today mainly Mellanox. Mellanox NIC cards actually dominating the market above 10 gigs. So if you see 25, 50, 40, 100, if you are buying from HP, from Dell, whatever, probably you have Mellanox card inside. And this is something that we are providing on the NIC card. But actually, if you are looking, this blue line here, it's not really a line, right? It's a network. At least 3 switches, right? Because you have top of rack, aggregation, and other top of rack. Probably even more sometimes. So there is a network here running between those 2 switches. But wait a minute, we don't have this TCP. It means that we don't have retransmission. It means that we cannot lose packets. Okay, this is the formula. And the reason is simple, because if we don't have TCP retransmission, it means all the packets that we are moving through the network should get to their destination. And this is very important, because the other requirements to have RDMA is actually to have a network that supports RoCE and RDMA. And there are different features to support that, to make the network what we call lossless or lossy. One of them is called ECN, another one is called PFC, flow control. So there are different protocols, but more important than that, you need a switch that actually configures the buffers, and those will not be debuffers. It cannot be in this environment because of the latency. So on-chip buffers configured for RoCE. Okay, and this is very important. And this is some benchmark that we did between Mellanox and other competition about how the switch acts on the pauses, where Mellanox is actually very smooth, while the competition is kind of working very hard. Another thing about RoCE and NVMe is that actually today, it's kind of in history. It's the first time the network becomes a bottleneck of the storage when it comes to latency. Why is that? So if we're looking at spinning disk, we're talking about latency of milliseconds. Not really relevant. If we are talking about flash, SATA SSD, we're talking about 100 micro. Again, not really relevant for the network. But then, if you look at NVMe, it's starting to be low. It's starting to be 10 micro, and Optane is bringing less than 8 micro. What does it mean? It means that if you are taking a 1040 gigabit switch, just off the shelf, based on Broadcom silicon, which is probably 90% of the market, the chip will do 8 microseconds for jumbo frame, which is usually the size of the packets when we are talking about storage. And that means that we need to remember we have 3 hops, right? Top of rack aggregation, top of rack. The accumulation is 24 microseconds. And 24 microseconds is actually more than our storage. So kind of things have changed. Now the network is becoming very important when it comes to latency. We have an advantage also there. We are doing 300 nanoseconds, the lowest in the market when it comes to latency. Another thing about Rocky and artificial intelligence is that with artificial intelligence, there is a master and there are slaves. And basically, the master is launching a task, and the slaves are always sending ACK, okay? Acknowledgement, acknowledgement, acknowledgement all the time. Those are small packets, 64 bytes usually. And you know what? If you're doing Rocky, as we said, you should not lose those packets. You should actually be sure that you can actually transmit them. And believe it or not, this is not so trivial. Again, if you are taking an off-the-shelf switch, he will drop the 64 packets. You don't have to believe me, just look at the data sheets. You can translate the data sheets and look that small packets are being dropped by switches. And the idea is simple. On Ethernet world, you can drop packets. It's not so bad because you have retransmission. But in the InfiniBand world, for example, where Mellanox came from, this is not allowed. So while Mellanox brought a disadvantage to the Ethernet world, there is an advantage also here on the Ethernet. We are not losing any packet size on full line rate. And the last very important part with Rocky is the microburst. So again, there is a master and there are some slave. And at some point, all the slave will respond to the master. This can create microburst. And for that, you need buffer. Again, not deep buffers, but just on-chip buffer and good ones and fair ones. And it's important, again, this is not trivial to have a switch that actually share the buffer equally to all the port and not having a situation when one port is getting more resources rather than the other ports when it comes to the buffers. So till now we talked about the Rocky part, which is more on the storage and machine learning segment. Let's talk about the VXLAN, which we'll talk a bit more about later on. So let's have a reminder about what is VXLAN. VXLAN is UDP packet. So if we are taking just traditional 10 gigabit NIC and plugging it on our server and running some layer 2 basic VLAN traffic, this VLAN packet will come into the NIC card, and the NIC card will do some basic stuff with it. It will do checksum, RSS, TSS, for example. But if we are going to run some VXLAN traffic, and this NIC card will be hit by a VXLAN packet, he will look at it. He will not understand what it is. And basically, as a thumb rule, everything that the hardware doesn't know what to do with, it's just pushing up to the software. So now software is going to do the checksum, RSS, TSS. And here is another thumb rule. If you are involving software in a 25, 50, 40, 100 gigabit, that means that your bandwidth is going down and your CPU is going up. So what you want to do here is basically have a NIC card that understands the packet and actually probe inside the packet to the right header and doing the same thing that it's doing with the VLAN, also with the VXLAN, the checksum, RSS, TSS. And then, again, there is another benchmark here showing that with a VXLAN offload, we're getting, this is a 40 gigabit, but it's the same as 100. We're reaching a line rate. And this line here shows the CPU. We're showing the CPU utilization the same as if we are doing VLAN versus VXLAN. And when do we need it? So we'll talk about it in a second, about VXLAN and VTEP and where exactly we're doing the termination. We can do it in different places, top of rack or hypervisor. So if you are doing it on a hypervisor, this is very important. So we talked about performance. Let's talk about network virtualization. So what happened in the industry in the last couple of years? Network has moved for kind of traditional, what we call 3-tier. There is a chassis out there and top of rack and maybe FEX and so on. to what we call scale out. That means that first of all, we're moving to faster network, moving from 10 to 25 for the compute, moving from 40 to 50 or 100 gigabit for the storage, and 100 gigabit between leaf and spine. Now what we see clearly is that even people that are moving from 1 gig to 10 gigabit, they will move from 10 gigabit to 100. They're actually going to skip 40 because it just doesn't make sense to run 40 where you can have 100. It's kind of the same price today. But anyway, there is the shift on the bandwidth, and this is very important in the AI environment and also on the cloud. And the second thing is that everything is virtualized, and the most popular way to virtualize your environment today is using VXLAN. So why VXLAN? First of all, VM mobility. Second thing is data center interconnect. Multi-tenancy, of course. As I said, customer brings their own IP. With VXLAN, this can be achievable. And I think today, and not today, but even before that, there is a good integration of VXLAN capabilities with the OpenStack environment. And when talking about VXLAN, there are actually two ways to do VXLAN. The first one is the controller solution. That means that you're using some kind of a controller. It can be Nuage or Midikura, OpenContrail. It can be Neutron by itself. But anyway, there is something here that is doing this kind of control plane for the VXLAN. And there is another option that is called the controllerless option, which is EVPN, which is using MPBGP to do this control. So if you are using the control option, then the controller, if it's NS6, as I said, or other controllers, can actually do the VTAP in two places. The first one will be the hypervisor itself. So in a virtualized environment, if you have an hypervisor, he can do the VTAP. VTAP is basically, in a nutshell, means that you are doing copying or mapping between the VLAN and the VXLAN. So NCAP, DCAP operation. It can be on the hypervisor, but sometimes, for example, in artificial intelligence, for example, workloads of machine learning, there is a bare metal, and then you need to do this VTAP on the top of rack. This can be done, as I said, by the controller. But if you have a large scale of bare metal, a lot of bare metal, then it's more, let's say, efficient and scalable to actually use EVPN. So EVPN basically today, and I will show you, and I will correct myself in a minute. Today, basically to do VTAP on your top of rack without the controller, this is EVPN, which is MPBGP, and this is basically to do that, and using, as I said, BGP to do this controlling, to do this VTAP on the top of rack. So now let's take those two concepts. We talked about Rocky on one hand, and we talked about the virtualized environment on the other hand, which is VXLAN. And we need somehow to combine it. How does it work? So if you remember on the physical network, I said there is those blue line, right? Those switches that are out there and they cannot lose packets. There are different features to make sure that that will happen. One of them is called PFC. The other one is called DCN, flow control, combination of those. But this information actually lies on the original header. And that means that if you are moving to VXLAN and you are doing the encapsulation of the packet, we are going to lose this information, the PCP or the ECN bits. So what needs to be done is basically copying it to outer header, and then afterwards on the decapsulation, moving it back to the inner header. This can be done by the NIC card or the switch. So this is an important feature that is needed for an AI cloud. And now, how are we going to do this orchestration? So we'll start with the first question, why should we do that? So it's very simple. First of all, we're providing something as a service. So we have some tenants with containers, VM environment, and we have the bare metal servers. This is the why. We need somehow to combine those two together. And how we're going to do that, we're going to go through some evolution of the ways that were advised or the ways that we did it in the past until the last solution today. The first thing that we did with the customer was to use actually a server running DBDK and do some kind of a mapping between the virtualized environment, this environment that is controlled, this layer 2 environment controlled by Neutron, to this EVPN environment. So running here VXLAN BGP EVPN. The problem with this solution is that it's eventually those are servers, network nodes. It cannot really scale. You cannot really reach the full line rate on full scale. It doesn't, it doesn't scale. So this solution was not good enough. The other option, well, today, if you're using controller, is using something that's called OVSDB to create this table, this mapping between VLAN and VXLAN. And then on the other way, EVPN is doing the same, creating its own tables of mapping between VLAN and VXLAN. So to actually marry those two together, we can put some switches here. And on one hand, the controller will do this OVSDB. On the other hand, EVPN will fill the tables and somehow will make sure that we'll create tables that will act as a gateway between those two components. To be honest, I didn't see a working solution till now with that. Maybe there is, I'm less familiar with. Another option is actually to use VRFs. And what does it mean? It means basically that we have switches. We are providing the customer what we call /16 subnet, but internally we are splitting it to two subnets of /24. And we are providing this /24 to each of those components, the bare metal and the virtualized environment. So we have the VM cloud and the bare metal cloud, and then the way it works is basically we're actually doing routing between inside this VRF, specifically for a tenant, between the two subnets. And this is basically a working solution today for some customers that are providing AI for artificial intelligence. But the future actually lies here. So today, actually, there is already support for what we call the bagpipe. Bagpipe is a component that is part of Nova Compute with an agent of Neutron. And basically, it means that it provides some basic functionality, not the full BGP, not a full protocol stack, but it provides some functionality for EVPN. And it can actually connect to BGP peers or by route reflectors, which is nice. It's just starting now. It's very, I think, immature, but it's, of course, it's going to grow. And eventually, when it's kind of, we'll drop the route reflector part and be able to do eBGP, then we know that we have a full solution, a good solution to deploy, and then there is no problem. Because then, basically, Neutron will continue to run with the ML2 mechanism driver, do the layer 2, but actually running EVPN will be done between the bare metal by the top of rack, but down to the hypervisor level that actually will be able to do this peering with bagpipe and EVPN. Okay, so this is the future. It's not far away from here, and it's in OpenStack. And of course, telemetry. So I'm going to finish with that. We have Rocky. We have VXLAN. It's always impossible to provide also telemetry. And I think the evolution of telemetry means that as long as your telemetry is more matured, it means that you can provide more value to the business. So if you have counters, for example, let's say you have counters on your switch, you can collect them, and you have counters on your NIC card, and you can collect them, but how exactly are you going to correlate between those two counters? I'm not sure. It's pretty difficult actually to do that. And eventually, it's not good enough. It doesn't provide any added value because we need to look on the application, be application-centric. So the next step will be end-to-end view, meaning there is some entity out there that actually will provide those counters, and everything will be available to the administrator, to the operation, to the end customer eventually. But also, that's not good enough because, again, this is not application level. It's still device level, but an end-to-end view. And the best way is to provide analytics. That means it's more application-centric. Just provide a full view of the workload, of the task, to see how it behaves. And this is the way we should aim to when we are combining this complex situation of virtualized VXLAN environment with RDMA Rocky running for the artificial intelligence bare metal part. This is kind of a view that we are providing through a tool that, or machine that we are calling Neo. Neo is basically software that is running on a VM or whatever, running somewhere, looking at the network, as a fabric. It's doing a lot of things. One of the things that he knows how to do is actually look at the fabric. He detects it automatically and shows the congestion flows. That means, and actually color them by some specific colors, showing that there is a congestion flows, and then you can actually drill down to the specific device, see where the drops are, and get this kind of important data. And beside of that, also being able to do kind of a dashboard with top congestion links and heat maps, which you can define, which can be high CPU utilization, high memory, drop packets heat map per threshold, and so on. Great, so I think that we are 4 minutes before the end. I'm very happy I gave you 4 minutes. If you have any question, about Rocky, about VXLAN. Okay, so I will thank you very much for your time.